acids and proteins, and then we did carbohydrates, simple sugars, complex sugars. Talked about how actually sometimes they attach to proteins too, so we did glycoproteins. Now we're doing, I think this is our last class of biological molecules before we get into the second half of the course, which is metabolism, where everything starts interacting. So what are we doing today? We're going to be talking about the lipids, and we're going to be going over the major classes of lipids: fatty acids, triglycerols, waxes, wax esters, phospholipids, isoprenoids. I don't know if that will get through all of that today, but we will. Tomorrow we'll finish up that, and then segue into talk about membrane structure a little bit. Okay, then various homeworks are due midterm on Tuesday. Any questions about where we're at? One other thing, actually, before I get into the fats, because David stimulated me on this. He was saying, where we were talking about sweeteners and the relative sweetness of different things, and he was asking how is that done, and is really where those numbers come from. And I just had a table in my notes, and so I was trying to find the source. I couldn't find the source of this table.
I found one.
Oh, did you?
Yeah, it's 30 times in this specific study.
In this one. But the other thing, so I was looking around too, and one of the things I was noticing looking around, maybe you saw it too, the numbers vary quite a bit, kind of from source to source. There's a large range. And so I actually, I found an article that talked about the difficulties of actually doing those kinds of studies a little bit. And I posted that up to Canvas if you're interested in that.
Yeah, and aspartame doesn't have anything on neotame.
Yes, I saw that.
Yeah, that was like 1,600 times.
Yeah, exactly. Okay, so lipids. Let's talk a little bit about the roles of lipids. First of all, the thing about lipids, most of our biological molecules we have defined based upon chemical structure. Water, obviously, H2O. Amino acids, they have the carboxyl group and the amino group, they're alpha amino acids. Then when we talked about carbohydrates, we define them as polyhydroxyaldehydes or ketones. Those are structural definitions. The term lipids really is a little bit more just of a general bucket and doesn't have a precise structural definition. It's more on their physical characteristics. These are molecules that are soluble in nonpolar salts. So if you think back in the early days of trying to figure out biochemistry, what are biological, what is living matter made of, you might do an extract. You might do extract it with a polar solvent, with a nonpolar solvent. And lipids are everything that is soluble in a nonpolar solvent. And so then what we have is a series of different structural types that we'll be walking through. In terms of role, they also have a variety of different roles. And so what I'm going to do is I'm going to show you some slides. It's kind of a little bit of an excuse just to show you the slides where we talk about the diversity of roles of lipids in biological organisms. And these slides relate to a necropsy of a sperm whale. Sperm whales are amazing critters. They're mammals, right? And they feed on giant squid like 2,000 to 5,000 feet deep. So they dive down 2,000 feet, right? And then they feed on these giant squid. There's no light down at 2,000 to 5,000 feet. So they have this complex sensory organ in their nose that use sonar to basically echolocate their prey, and then they eat their prey, and then they come. Anyway, they're pretty cool organisms. A dead one washed up several years, probably a couple of decades ago, maybe a decade and a half ago now. A dead one washed up on Point Reyes. And the Marine Mammal Center is an organization that treats sick and injured marine mammals and tries to, they have a veterinary program, and they basically will treat the marine mammals and throw them back in the ocean. And some of that is to directly help the marine mammals, but a lot of it is to try to understand what are the things that are impacting the health of marine mammals, to get an idea of what the ocean health in general. So not only will they treat sick and injured marine mammals, but also if something like a whale washes up, they'll perform a necropsy to try to understand why it died. And so these pictures that I'm going to show you are of a sperm whale necropsy, and in the process you can basically see all the places that lipids exist within the whale and what some of the roles are of the lipids. So here's an example. They're starting the necropsy here, and so what they're doing is they're peeling off the blubber layer of the whale. Okay, and so the blubber whale is a fat, and it is a triglyceride. And so here's an example of the structure of the triglyceride here, and we'll be walking through those a little bit. And you think about the role of that. In the case of a whale, there's a couple different roles. One is energy storage, and the other one is thermal regulation. The ocean is a cold place. These are mammals, they're warm-blooded animals, and so it provides an insulation layer. There's another whale, commonly seen off the California coast, that kind of show you sort of the different role of fat as energy storage, and that's the gray whale. And what the gray whale does is it feeds in the summertime, northern hemisphere summertime, it feeds up off the coast of Alaska, Bering Strait, basically, on krill up there, and it basically does most of its feeding for the year when it's up there. And then come late fall, it'll start migrating down along the Pacific coast, along California coast, and it goes down to Baja there, and then there's some lagoons down there, and that's where they in the lagoons down there, that's where they breed and they give birth, and then in the early spring, early to middle spring, they go back up north and go back up to Bering Strait and feed. So the energy that they get up in the Bering Strait has to survive them basically for the 8 months or whatever that they're on this long trip. They will stop and feed occasionally on the way, but most of the calories here. Actually, in thin krill years, when they're not getting a lot of krill and they're kind of skinny on the way down, sometimes they'll really try to stop. They're basically getting pretty hungry, but they haven't gotten to the feeding grounds yet, so they'll stop to places. And sometimes they'll come into the San Francisco Bay looking for food, basically. Anyway, that's gray whales. And the role of the triglycerides, that lipid, is energy storage and thermal regulation. Let's see. Here, what are we doing here? Oh, now we're starting to actually get in. They're going to look at the digestive tract in here, and eventually I think I know actually, I know what it's going to talk about is what I have here. So this is the front of the whale. This is the lower jaw. This is the largest toothed whale. So this is has teeth because it's going to be eating those giant squid down here. Then up here is the spermaceti organ. That's this organ that is basically an echolocation chamber. And it is filled with, actually let me go back to this. So that's what's up here. And it's filled with a special lipid. It's a wax. It's a wax ester. So it's a carboxylic acid esterified to a long chain alcohol, and that's what fills up the spermaceti organ, this chamber, this echolocation chamber. In the whaling days, that was one of the most valuable parts of the whale, because it turns out that is highly valuable both in terms of its lubrication properties, so to use as an industrial lubricant, and also in terms of its in oil lamps, whale oil lamps. It basically burned really bright and clear, and not a lot of smoke, and so it was a good quality fuel for whale like this. It also has a consistency like human sperm, and that's why it kind of looks and feels like human sperm, and so that's why the whole the whale gets its name. It's the sperm whale. It's from this stuff, this wax ester that's in there, and that's why it's called spermaceti oil. Okay, now we're getting into the gut a little bit here, and this is the small intestine coming out here, and so the whale eats primarily these giant squids, and it can digest almost all of the squid, except there is one part called the squid beak that's actually made out of chitin. Remember, we were talking about chitin, the same thing that's made up of insect exoskeletons and fungal cell walls. Chitin, and it doesn't digest that. And this part of the giant squid will accumulate at the bottom of the stomach at the entrance to the small intestine. And as it accumulates there, it will begin to be covered with another lipid. It's this lipid right here, and it's known as ambergris. That lipid will cover the accumulated squid beaks and kind of get it all greasy, and that's going to allow it to pass through the intestinal system of the whale, and then when it comes out, it floats to the top. Now, it turns out this molecule here, traditionally and still is, highly valued as a perfume fixative. Now, what's a perfume fixative? Well, when you make a perfume, you like to, you have the whatever fragrance molecules in there that make you smell nice, kind of thing. But those molecules are highly volatile, and if you just took a straight solution of that and put it on your skin, it would volatilize right away, and you would smell really great for a short amount of time, but then it would be gone away. What you really like to do is take your fragrance molecules and put them in a solution with a compound that'll kind of dissolve them a little bit and release them more slowly so it lasts longer over time. That's what's known as a perfume fixative. It turns out that this molecule makes a great perfume fixative, and it also has, even though it comes from the intestines of a sperm whale, has a pleasant odor in itself. And so, I think most perfume fixatives these days are some sort of synthetic compound, but this is what was used traditionally, and it still is occasionally used, and people will search for these blobs of ambergris will wash up on beaches and stuff. People will look for them, and if they do, they'll collect them and they can sell them. There's a market for it, and you can get like thousands of dollars for one of these blobs of essentially, a part of whale poop. Anyway, so those are some examples of the diversity of the different functions of lipids. All right, so now what we're going to do is we're going to move on and start talking about the different classes. We'll talk first about the structural types. And the first structural type we'll talk about are the fatty acids. And actually, I think I want a whole board sorts of stuff, so I'm just going to leave that there and start a new board. So, fatty acid, the acid part, what's the functional group? It's kind of like amino acid. What's the functional group in an amino acid? A carboxyl group, right? So it's the same kind of thing. We've got a carboxyl group. And I'm going to go ahead, let's see. I'll go ahead, and I've been doing this pretty consistently. Draw it like it would be drawn under physiological conditions at pH 7. The pKa's of these carboxyl groups are going to be around 4 someplace. Physiological conditions around 0.7, so that they are around 7, so that when the pH is greater than the pKa, it's the deprotonated form. And so I'll do this. And so the first fatty acid I'll introduce is one that has 16 carbons. Most of the fatty acids have either 16 or 18 carbons. There's some fairly regular exceptions to that, but most of them are 16 or 18 carbons. So we're just going to talk about the one that has 16 carbons first. And so we're going to go, this is carbon 1, 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. So now we have, so it's a 16 carbon fatty acid. Now there's a nomenclature that is used to describe fatty acids in which you indicate the number of fatty acids and then the number of double bonds within that fatty acid. So in this case, it has 16 carbons. And there are no double bonds in the chain. You don't count the double bond part of the carbonyl, because you're talking about the double bonds in the chain. So this would be 16, 0. So again, that's the number of carbons. And then this is the number of double bonds. This molecule has a common name, and that common name is palmitic acid. Or as I'm having trouble here because I wrote it as palmitate, but I'm writing it as palmitic acid. But I'm going to go ahead and stick with palmitic acid because that's what people tend to use more often than palmitate. And it has that name because in the triglycerides of palm oil, you tend to have a lot of this 16 carbon fatty acid. Because this molecule doesn't have any double bonds, it's known as a saturated fatty acid. Now there's a very analogous, I'll just do this one quickly, there's a very analogous one in which we have a carboxyl group that has 18 carbons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So just another 2 carbons. Almost all naturally occurring fatty acids have even number of carbons. Odd chain fatty acids are rare. So what's this nomenclature going to be? What, because 18, still no double bonds, 18, 0. And then this has, common name is stearic acid. And the stearic acid becomes, because it's relatively common in the triacylglycerols, the fats of cow, so beef fat. Beef fat, what's that? Tallow. Isn't tallow beef fat? All right, another really common one is 18-1. So it's 18 carbons with double bonds. Now where is that double bond? It's right in the middle. So it's at the number 9 position. So we go 2, 4, 6, 8, 2, 4, 6, 8, 9. Then there is a double bond. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, there could be multiple fatty acids with one double bond where the double bond is just in different positions. So to be more precise in our nomenclature, we would add to this, the position of the double bond is delta 9. Sometimes that delta 9 is actually done as a superscript. And that's because if we count the numbers here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. That double bond is at the 9 position. This is oleic acid. What else was I going to say about this? So these, are saturated because there are no double bonds. This is unsaturated because it has one double bond, and more precisely, it's monounsaturated. It's a monounsaturated fatty acid because it has one double bond. It gets its name oleic acid because it's common in the triglycerides of olive oil. All right, now we are going to add some more double bonds. We're going to stick with 18 carbons, but now we're going to go 18, 2, delta 9, 12. So we're going to have two double bonds, one at the 9 position and one at the 12 position. So 1, 2, 4, 6, 8. Then we have, again, this is at the 9, 10, 11, 12. This is the 12 position. Another bond, double bond, 12, 13, 14, 15, 16, 17, 18. So now we have the two double bonds. Oh, this is linoleic acid. Here, I'm going to make sure we can keep these straight. So this is linoleic acid. And it is a polyunsaturated fatty acid because there is more than one double bond. So we're introducing some terms that are relatively common in the nutrition literature, and healthy fats are polyunsaturated fats. They have these fatty acids that have these double bonds in there. All right, we're going to keep going in complexity here. We're going to add one more double bond. And this we're going to 18, 3, delta 9, 12, 15. So 2, 4, 6, 8, 9. 12, so this is 9, 12, and we have one more here at 15, 16, 17, 18. So this one is alpha linolenic acid. Linolenic acid actually refers that has the 3 double bonds. but and the alpha refers to specifically double bonds at those positions. There are other like beta gamma linolenic acid that actually have double bonds in different positions, but this is alpha linic acid.
Question.
Yes.
So pertaining to these specific acids, if the double bond's in a different place, is it the same acid or is somebody else?
So it is going to have, usually it will have some sort of modifier to this. So this, for example, linoleic acid, this is the most common one. If you refer, people kind of assume you're talking about the 912. If you want to, if you put the double bonds at different positions, then it has some other modifier to it. And I can't think, I'd give you an example off the top of my head, but I can't think of one. Okay, now I'm going to introduce you a different type of nomenclature. This is a nomenclature that instead of referring to the position of the double bond from the carboxyl carbon here, 9, 12, and 15, actually refers it to the other end. So this far end of this fatty acid, this is known as the omega end. So we can define the position of this double bond not based upon this the numbering of this carboxyl group, but the distance from the omega end. And so alpha linoleic acid here has a double bond 1, 2, 3 carbons away from the omega end. So this is known as an omega-3 fatty acid. And you've probably heard of omega-3 fatty acids and health claims for those.
Do they do that with all of the double bonds?
No, so usually if you refer to omega-3 fatty acid, it's a fatty acid that has a double bond 3 carbons from the end, and it may have other double bonds as well. So this linoleic acid here, this is 1, 2, 3, 4, 5, 6. This is an omega-6 fatty acid.
Is the alpha linolenic acid also considered an omega-6 or no?
No, so you would call this omega-3 versus the omega-6.
So-
And this will make a little bit of sense. In just a second, I'm going to get into some talk about some of the health claims related to omega-3s and omega-6s. in just a
Okay.
sec. Okay, so the other aspect, why I kind of left some space over here, is to talk about the influence of the presence of these double bonds on the physical characteristics of the fatty acid. So basically, the more double bonds you have in there, the lower the melting point, the more liquidy it's going to be. So if we look at the melting point, and this is in degrees Celsius. For palmitic acids, it's 63.1. So 63, like how hot is that? This is 63.1. How hot is it out today? Outside, in Celsius? Did it get there?
Maybe 30 or something.
What's that?
That's 2/3 of water boiling to give it a contextual color.
Yes, exactly. So that's 2/3. Outside today, if it gets up to 90, 98, it's going to be 37 degrees Celsius, right? So it's pretty warm. Room temperature in here, well, it should be like 19 or something, but it's probably like 23 because it's a little warm in here. It's like this. And so 63, you got to heat it up. It's not boiling temperature, but you got to heat it up before it's going to melt. So if I brought in some palmitic acid here, should have done this, it's going to be a solid. It's going to be a solid. Okay? I'll skip over stearic acid. Oleic acid, introducing that one double bond changes, greatly lowers the melting temperature. So this is, the melting point of oleic acid is 12 degrees C. So if I brought in oleic acid in here where it's 20, 21 or 22 degrees C, it's already going to be a liquid. And if we introduce more double bonds for the linoleic acid, it's -5. And for the alpha linoleic acid, it's -11. But the big change was just introducing any double bond. So introducing any double bond really changes the physical characteristics of the fatty acid.
Does changing the number of carbons in the chain change anything about the melting point, or is that?
It'll change a little. I wish I had that number, but I don't have it handy. Somebody could look up for me, melting point of stearic acid, we can get it down there. My guess it's gonna be within 5 degrees of that.
Will it be
Can you look it up for me?
Oh, no.
No, oh.
I was just gonna ask, why are all the double bonds in cis configuration?
Okay, so I was gonna get there.
Is it like thermodynamics?
No, it is, so I guess the best answer to that, most of the biological double bonds in fatty acids are cis. Almost all of them are cis. I'm going to show you in a little bit when we start talking about hydrogenation of fats, that you can introduce trans double bonds. When you introduce a trans double bond, okay, it actually greatly changes the physical characteristic of the fat. It actually makes, so trans oleic acid is much more similar to palmitic or stearic acid in there. So it kind of reduces this effect. The idea is the cis double bond introduces kind of a kink in the chain, like if my carboxyl group is here and my chain is hanging down here, it kind of introduces a kink in the chain, and it makes it more difficult for everything to pack together. Yeah, did you get a melting point?
Yeah, about 69 degrees Celsius.
It's okay, 69. Okay, so the introduction of an extra couple of carbons doesn't impact it really much, but the double bond is really going to impact it. So I do kind of want to highlight that point. I'm going to get here is that this is a cis double bond. All right, now I'm going to introduce you to another class of fatty acids known as the eicosanoids. Eicosanoids because they have 20 carbons. I'm going to introduce you to two different ones. The first one is arachidonic acid. Arachidonic acid is 24 delta 5, 8, 11, and 14. So what's that look like? Here's our carboxyl group. 2, 3, 4, 5. 5, 6, 7, 8, 8, 9, 10, 11, 11, 12, 13, 14, 14, 15, 16, 17, 18, 19, 20. That's arachidonic acid. So this is an omega-6 fatty acid because it has a double bond 6 carbons away from the omega end. So this is a biosynthetic precursor to eicosanoid signaling molecules. So it generates icosanoid I'll show you the pathway in just a sec. These are molecules with names like prostaglandins, thromboxanes, leukotrienes, prostacyclins. If anybody's taking one of those signaling, classes on signaling molecules, some of those names like this. This is actually this. Remember, I was talking about the cyclooxygenase, the enzyme that is inhibited by the non-steroidal anti-inflammatory drugs, the aspirin and all of that. This is the substrate actually for that reaction. And that's part of this pathway to make these icosanoid signaling molecules. These tend to be pro-inflammatory. Now, I'm going to contrast that with another icosanoid, which is known as eicosapentaenoic acid, or EPA. What it is 25 delta 5, 8, 11, 14, and what's the next one? 17. So it has a very similar structure to this. Except now there are 5 double bonds. That's a structure. And now this one is an omega-3 fatty acids. So this generates icosanoid signaling molecules that tend to be anti-inflammatory. Okay, so this kind of leads to a model relating omega-3 fatty acids to cardiovascular health. It was found as part of just nutrition studies that cardiovascular health, reduced risk of having a heart attack was associated with high consumption of fish in your diet, and fish tend to have a lot of omega-3 fatty acids. So fish oil have a lot. So people were eating a lot of fish in their diet, were getting a lot of omega-3 fatty acids, and relatively low omega-6 fatty acids versus a land-based diet. And those people tend to have lower risk of heart attack. And so the thought that this might be causal, that actually the presence of these omega-3 fatty acids would actually promote the synthesis of these anti-inflammatory signaling molecules and provide a cardiovascular protective effect. That it wasn't just a correlative thing; it was a causative. It was a causative thing. And so there was a lot of research being done on omega-3 fatty acids. In a little bit of my history, when I was working in industry, I was working for Monsanto over in Davis, and there was a big project over there to try to see if we can't genetically engineer land plants, so like canola oil or soybean oil, to actually generate these omega-3 fatty acids. Because these omega-3 fatty acids, that if you started taking everybody in the world and feeding them fish oil, there just isn't enough fish oil out there to feed everybody. So we basically wanted a land-based source of omega-3 fatty acids to provide all these cardiovascular benefits. And so there was a big project and Monsanto and other plant biotechnology companies to be able to do this, and there was just a lot of work in general. The problem is that when you do clinical trials of interventions where people take fish oil pills with defined amounts of these omega-3 fatty acids, there isn't very much strong evidence that it actually does any good. Doesn't that people do any harm? There's no evidence that it does people harm, but the largest, most complete clinical trials suggest no effect. And actually, so companies like Monsanto, they just abandon it like crazy. It's like, well, it doesn't have effect. But you still see, there's still, from a marketing standpoint, there's a lot of promotion of, these healthy omega-3s. And then people also will talk about, well, maybe if it doesn't have cardiovascular effect, then, maybe there's some influences on brain health, on some other things. Which there could be. It could be because they haven't measured any particular effect. But you also kind of have to understand how science works a little bit. And that if I'm an assistant professor, or if I'm a project leader at a company that is trying to understand the omega-3s and trying to develop a product that would improve cardiovascular health, I have no interest in any data that shows that it actually has no effect, right? And so, so what you tend to see in the literature is basically the people who are published on that, the people who have a lot of vested interest in showing that it actually has effect. And nobody likes a party pooper, basically, that can come in and say, actually, this isn't doing anything, right? And so, so the literature tends to have a bias for positive effect on, I'm just giving this as one example. You'll see this a lot with compounds that make nutritional claims, that there's sort of a fundamental bias. Yeah?
I just thought of one that was extremely recent. It happened recently with psilocybin, the hallucinogenic.
Oh yeah, okay, yes, yeah, okay. I'm not familiar with that one, but I would believe it. I'm going to give you another example, HDL, a little bit. HDL is a therapeutic molecule as well. So it is possible that still there might be some kind of effect with some certain subpopulations, or if you get the dosage just right and all that. And that's the sort of things that the people will come back with. But it's also possible that it really doesn't make any effect, and nobody wants to give up something that they've been working on for 10 or 15 years and say, oh, actually, I guess that was all for naught. That's not an easy thing to happen. Suzanne, Kareem, is it Kareem? Are you there? Kareem? Yeah, they're like this. We had a whole class on this sort of stuff. Kareem took a class. I teach a class of science in the public good that talks about the process of science, and talk about how this is kind of an interesting little tidbit here. You think of science, it's the the objective analysis. It's a nice, reliable source of truth. But if you looked at published journal articles in good journals, not crappy journals, but in good journals, and studies where people have gone back and tried to actually reproduce the findings in a published, peer-reviewed journal article like this, it's about 50%. About half of them will reproduce. So about half of them don't reproduce, and about half of them do. And so in this class, we get into a lot of the reasons why is that. What is what are the inherent biases that lead to people to publish reproducible results? All right, that's a little sidelight. Where we are, we got the I could probably have a few slides to illustrate this stuff too. We're going to like this. Okay, so again, emphasizing the importance of the cis double bond on the overall structure of the fatty acid, and then ultimately the physical properties. By having that double bond there, it puts a kink in the chain, and then that kink will basically prevent those lipid tails from packing together, and that results in a decrease in melting point. The trans fatty acids. Should I talk about this now or a little bit later? I'm going to come back to this. Yeah, I'll come back to that one. So the anti-inflammatory prostaglandins are synthesized from these 20 carbon fatty acids. Again, this is the whole story. It's like, I'm adding some examples of the signaling molecules. So here's arachidonic acid. So this is the one that has that is the precursor to these inflammatory prostaglandin signaling molecules. Again, cyclooxygenase is cyclooxygenase is one of the enzymes involved in that conversion, and so that's why those are anti-inflammatory drugs, because you're blocking the production of these inflammatory signaling molecules. The EPA down here gets converted to these more anti-inflammatory. It makes a really nice story. It makes a really nice story. Oh, actually, I gotta do this too, because this always drives me nuts. The other thing is labeling. Okay. So we notice that this is alpha-linoleic acid is an omega-3 fatty acid, right? And then, but then the EPA, the one that's thought to have the biological effect, is this EPA in there. There's also a 22 carbon version that has a similar kind of thing. This omega-3, in order to have the potential protective effect, has to be converted to that one. That conversion efficiency isn't very low, or isn't very high, right? So what you really want to do is you want to eat fish oil that has this rather than alpha-linoleic acid, because this isn't going to convert to that in very high efficiency. Essentially, the health benefit is going to be less than the health benefit of that. But that isn't necessarily reflected in the labeling. So if you buy your eggs and the eggs say, omega-3 enriched, so what they do is they will work into the chicken feed. They'll work in some sources of alpha-linoleic acid. Flaxseed oil is one particular. So they'll incorporate those other oils in there so that the fats that accumulate in there have higher amounts of omega-3s, right? But it's the 18 carbon omega-3 rather than the 20 carbon omega-3, and so that 100 or 200 milligrams per egg or whatever the omega-3 really isn't going to have much of a health effect, because it still has to be converted to that. The sorts of studies that they do to look at potential health effects here is give people like a gram of this stuff. So, 100 or 200 milligrams of this isn't really going to really impact that very much. That's just another sort of buyer beware aspect of health claims on foods. Nope. Nope, that's all. I didn't need to do that. Where are we at? Okay, let's go ahead and take a break, and we'll come back.